Let's take a look at section 10.2 on using the fundamental counting principle. As you remember, in 10.1 we used what was called systematic listing as a means to figure out the number of ways something could occur. And it works, okay, but sometimes it can be very time consuming, such as in the case of our last example where we had 120 possibilities. So there is a much faster way, a quicker way to do this, and one of those ways is to use what is called the fundamental counting principle. The fundamental counting principle says when a task consists of two parts and the first part can be done in m ways, while the second part can be done in n ways, the number of ways to complete the two-part task will be m times n. Now you can expand the fundamental counting principle and add a third part, say it can be done p ways, then the three parts can be done in m times n times p. And we can continue to add 4 parts. We would be multiplying 4 different numbers, 5 parts to 5 different numbers, and so forth. So it's relatively easy to do. All we have to do is to be able to multiply. So let's look at some examples. It says, if you consider the problem of rolling 2 fair dice where one is red and the other is green, the red die has 6 possible outcomes and the green die also has 6 possible outcomes. So when we look at the two-part task of rolling both dice together, there are 6 times 6 or 36 possible outcomes. So as you can see, that's a lot faster than drawing the table we did in section 10.1. Okay, so as I mentioned, the fundamental counting principle as stated in the text has been expanded to cover tasks with more than 2 parts. Okay, so example 2. Consider the restaurant problem we did last time in 10.1. A meal consists of a salad, which had 2 choices, meat, where we had 3 choices, and a vegetable, where we had 3 choices. With the fundamental counting principle, we'll have 2 times 3 times 3, or 18 possibilities, which is what we got when we made the tree. Remember, it was kind of hard to squeeze it in. I had to move one section over to the right in order to fit it all in. But in the end, when I counted all the possibilities, I got 18. So as you can see, it's a lot quicker to apply the fundamental counting principle. Okay, example 3. Consider a student who has an early class. Since he is half asleep when he dresses, he selected 6 shirts, 4 pairs of pants, 8 pairs of socks, and 2 pairs of shoes that all go together. How many outfits are possible when he randomly selects a shirt, pair of pants, a pair of socks, and a pair of shoes? You're to use the fundamental counting principle to solve the problem. So pause the recording, figure out your answer. Once you have an answer, then you can restart the recording to check your work. Okay, I'm assuming that you have come up with the answer to example 3. Our student has 6 shirts times 4 pants times 8 pairs of socks times 2 pairs of shoes. Okay, and let me get my calculator here. Okay, I'll just do it by hand. 24 times 16. Okay, so what I did was I multiplied these two, and now I'm going to multiply these 2 answers together. 4, 2, and I'm coming up with 384. 24, 14, I always like to check my work. 4, 8, 384 different outfits. Okay, so that's a lot of different possibilities for that one. All right, consider the problem involving selecting 3 officers from a club with 6 members. We used an alphabetical left to right method. That was that long one, listing the possibilities, but we quit because it was taking so long. So, with the fundamental counting principle, what we see, there are 6 choices, A through F, for the president. Once the president is selected, we have 6 choices for the president. There are only 5 choices left for the secretary. So we've now removed 2 people. One's the president and one's the secretary. So we have 4 choices for the treasurer. So we get 6 times 5 times 4, or 120 possibilities in all. Wow. Way too many to want to list out. Okay, example 5. Suppose that a state decides to use 3 letters followed by 4 numbers to create license plate numbers for the state. How many different plate numbers could be created using this setup? So we use the fundamental counting principle to answer the question. We have 3 letters followed by 4 numbers. So assuming repetitions would be allowed, we have 26 choices for each of the letters. We could have AAA if we wanted to, or ABC or whatever. And for numbers, we have 0 through 9. This is A through Z. We have 10 choices. And 10 choices for the last one. So what we have to do is we have to multiply 26 to the 3rd times 10 to the 4th to come up with our final answer. And I'll let you actually do that. Okay, so you want to cube 26 and then multiply it by 10,000, it looks like. Okay. Now, the factorial formula. Some cases, such as a case where you're looking at having a series of books or seats, and you're filling up all the books or all the places for the books or all the seats, use what is called a factorial formula. So let's take a look at that. It requires us to learn a new symbol. A factorial expression is indicated by an exclamation mark, and some common factorials are listed below. 2 factorial, we start with 2 and we multiply by all of the decreasing whole numbers down to 1. Okay, so 2 times 1. 3 would be 3 times 2 times 1. 4 factorial is 4 times 3 times 2 times 1. 5 factorial is 5 times 4 times 3 times 2 times 1. And 10 factorial, we multiply all the numbers from 10 all the way down to 1. So you can see the products that we get for those. And most scientific calculators do have a factorial button. On the TI-83 or 84, you can go to the math button, go across the top and select probability, and then select the factorial symbol and press enter. So what you would do on the TI-83 or 84 is enter a 5, for example, then choose math, probability, the factorial symbol, and then press enter. So let me see if I can get to that fairly quickly here. If it'll open up quickly. We'll do the 5 factorial. Okay, so let me clear this. And what I want is to do 5 factorial, so I'm going to press the 5. Then I'm going to go to math. And I want to go across to probability. Okay, so there's probability. Whoops, I went one too far. Here's our factorial is number 4, so I'm going to choose 4. And then press enter. So that's the way the TI-83 or 84 would work. Okay, let me go back to my lecture here. We're almost through. Okay, so suppose you have 7 books and there is a space on your bookshelf for all 7 of the books. How many ways can you arrange the 7 books? And it would turn out that you could arrange them in 7 factorial ways. So you're going to multiply 7 times 6 times 5 times 4 times 3 times 2 times 1 on your calculator, or if you have a special factorial key, you can use that. All right, so let's look at example 2. Suppose 12 friends go to the movie theater and find 12 seats in a row where they can all sit. How many ways could the 12 friends be arranged in those 12 seats? All right, so if we think we have 12 places, 12 seats, so in the first seat there are 12 possibilities, second one 11, 10, 9, all the way down to 1 seat left for the last person. So we're going to end up with that being 12 factorial. And I'll leave it up to you to either multiply out 12 times 11 times 10 all the way down to 1, or enter 12 factorial on your calculator to come up with the answer. Okay, and one last definition before we leave this lecture. 0 factorial is defined to be 1. 0 factorial is defined to be 1. So that concludes the lecture on 10.2.